Not going to get one laugh out of that? Man, you guys suck. Oh, yeah. Let me check something. I ran out of my 238 gig hard drive was full. I'm trying to delete a bunch of files, move a bunch to my Google Drive, so I think we'll have enough. We should be good for today. Alrighty, so here we go. And let's begin. I don't know, we're at 54. So we got about 50. Yeah, you lost a penny. Alrighty. What?
I'll pay you tomorrow. I gotta go to school anyway.
Okay, I won't be here. I'm only here on Mondays, Wednesdays, and Fridays. Alrighty, so it is, we already discussed 420. This is going to be Chem 1110, Chapter 13, Day 2. And our objective is going to be able to better understand, and this is what we're going to do. We are going to better understand addition, hydrogenation, halogenation, halogenation, and hydration. Alrighty, now what we're going to do today is we are going to review a little bit, and then we're going to go into these 1, 2, 3, 4, 5 different kinds of reactions. Okay? Now, what we've got is we've got addition reactions. We've got hydrogenation reactions. Sometimes they call it that, hydrogenation reactions. We've got halogenation, which is actually something we've talked about in the past. We have hydrohalogenation, and we have hydration. Okay? And all of these are very similar, okay? Though they are not the same, so we will have to go through that, okay? Now, before we go on, I do want to go through a couple of review questions from naming from the other day. Okay? You ready to rock and roll? Okay, so this is what we got. Let's say I got this. Okay, let's say I've got that right there, and I wanted you to name that. Who can remember where I need to start naming this?
Branch.
I start on the branch. Okay, I used to start on the branch.
You start on the alkene.
I start now. If you recall what I said, that the double bond now takes what? Now it takes precedence. Now, if I had a branch of that double bond, then I would definitely want to start there. But here I've got two options. I've got 1, 2, 3, 4, 5, 6, right? Or I have 1, 2, 3, 4, 5, 6, right? Now, when I do this, which one is going to give me the lowest sum? The red numbers or the blue numbers?
Blue.
The blue numbers, right? Now, because I always start with the double bond, I won't need to signify where this is at, right? And this will become, well, first off, what is this branch? That's an ethyl, right? This is a methyl. Which one's going to come first? The ethyl, because it's alphabetized. I'm going to write 4-ethyl, right? Dash 3-methyl. And then that's going to be, what's that? Cyclo what?
Excellent.
Hex. What'd you say?
Ene.
Hexene. Yep. And I don't have to put a 1 there because it is always on the 1 when there's 1. Now, let's say I did this. I don't think I discussed this the other day. Let's say I've got that. Let's see, I now have this. Let's say I do that. Okay? Now let's say I do that. Now, I still have to cross a double bond first. But because I've got multiple ones, I now have multiple options here. Okay? So, because I've got a branch and a double bond in the same place, I definitely want to start there first. Right? But I can really see a couple of options here. Okay? Now, I've got to start at a double bond and a branch, and I always have to cross the double bond first, right? So knowing that, I would go 1, 2, 3, 4, 5 is one option. Started at my double bond and a branch, cross the double bond first, correct? Now, how else could I have done this? Where I maintain those same rules. Started a branch double bond combo and cross the double bond first.
You could do that at the number 3.
Yeah, I could start and I would have gone 1, 2, 3, 4, 5 like that. Is that what you're saying, Tolman?
Yeah.
Okay, now.
And, what about alphabetical order?
Say that again.
Alphabetical order?
Alpha.
It doesn't matter, like, which one goes first, but usually you want to do the alphabetical order. You're right, but in this case it does matter because here I'm going to get a 1 and a 3, right? Yeah.
The red way I would get a 1 and a 4. Some rules. Does that make sense?
Yeah.
Okay, but you're right because this is a propyl and this is a methyl. If the sum was the same, then I would have started here. But because the sum is different, the sum is going to take precedence. Does that answer that question?
Yeah.
Now, because now I have 2 double bonds, now I have to number them. Okay? So, we're going to go with the red, or we're going to go with the blue ones because that gives me my lower total sum, right? So, red's gone, and this is what you're going to have. You're going to have 3-methyl, okay, -1-propyl, right? Now, this is where this kind of becomes a little challenging, is because now I've got 2 enes, right? So this is going to become a what?
A diene?
A diene, exactly. Okay? And that diene is going to happen at 1 and 3. So right here I got 3-methyl-1-propyl. Then it's going to be this. It's going to be 1, 3 dash cyclopentadiene. The di, meaning there's 2 numbers there, meaning I've got 2 double bonds. And the numbers come out front of the cyclo, not in the middle. Does that make sense?
Yes.
Okay. Now, let me look at one thing here. It was...
Hey, Dan, I saw the video from last year. I watched that.
Okay, was it pretty good?
Yeah.
Okay. Were you not on last time?
No, my computer wasn't working.
Oh, okay. Did you get all that sorted out?
Yeah.
Okay. Yeah. I think... I don't remember. I'm looking back over the test really quick. I don't remember them doing anything too complicated when it came to something like this. I was just making sure that there wasn't anything too bad. There's not. I haven't gone through the whole thing, but just this portion. I think we're okay there. Does that make sense, though, how we have to put the number of double bonds out here and then the di, and I mean it could be a di, a tri. They're not going to get very complicated here, but that's about, I would say that's as complicated as you're going to see. Does that make sense? Now they could do that with a straight chain as well. Like let's say I did this, like that, and I did this, and I did that, and I did this, and I did this, that. Okay, let's say I had that. Okay? Now, I want to name this one. I first got to start, right? And I want to make sure I'm going to have, what, 2 branches and 2 double bonds, right? Now, because this isn't cyclical, I've just got to start at one end or the other end, right? But I still want to try and have my sum of my numbers be the what? I heard it, very faintly, but I heard it. The smallest possible, right? So if I look at this, I basically only have 2 options, don't I? I got 1, 2, 3, 4, 5, 6. Now someone's going to say this is a 7, right? Because when I drew this as basically a branch, right? But what do we learn?
Longest possible chain.
Longest possible chain, right? So it's going to go 7, 8, 9, 10, correct? So no matter what it is, this is going to be some kind of deck, correct? Yes? Or no? Yeah. Okay. Now, if I went the other way, I went with red, I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Well, if I look at these numbers wise, the red one, right, would give me a 5 and a 5, right? Because I got a 5 branch and a 5 dot, and a 5 een, right? And then it would have given me a 7 and a 7 to get all those branches, right? Does that make sense? 5, 5, 7, 7. But if I go with my blue ones, this is going to give me a 3 and a 4, right? And then a 5 and a 6, correct? So I always number the double bond with the first number. Well, this sum is, what's that, 18? This sum, though, is 24, right? So wouldn't I go with the blue sum? That's going to give me the lowest possible sum, correct?
Yes.
Okay. So then, I'm going to get rid of the red numbers because they don't matter, because they're wrong. Now, I've got a methyl there, and I have a methyl there, so this is going to become a what? A dimethyl, correct? So I'm going to be 4, 6, right? Dash dimethyl, correct? 4, 6 dash dimethyl dash what?
3, 5.
3, 5 dash decadiene, just like that. Who was that?
Tolman.
Good job, Tolman. That makes sense or no?
Yes.
Okay, alright. So that's a little bit of review from the other day, and now we're going to go on to today's stuff. Now, we're going to basically walk through at least one example of every one of those words I discussed. Okay? Now, addition reaction. And addition reaction. Okay? And if you go back to my objective, I probably should have specified this. Each one of these four are all different types of addition reaction. Okay? In an addition reaction, okay, elements are added to a compound. Okay? Now, for what we're going to do right now, okay, they're going to be added to a compound at the double bond. Okay? And what that means is this. Let's just take an easy one like this. Let's say I take what do I got here? I got butene, right? I got butene. Now, because it's in the first spot, I wouldn't even need to label it. Okay? If it's not in the first spot, then I would need to label it. It's kind of like what in that sense? Anybody draw a parallel to anything you know when it comes to that? Okay, I heard that. Say it out louder so everybody can hear it.
In math, you have X, not 1.
Exactly, okay. Russell, is that you?
Yeah.
Yeah. Okay, so, not only you know my voice, I know your voice. So, now, let's say I add, and we could go through each one of these. So what was the first word I gave you besides addition? They give you halogenation?
Hydrogenation.
That was the first thing after addition I gave you? Okay, so hydrogenation. Okay, so hydrogenation equals adding H2. Okay, I'm just going to add H2. Typically, you need a catalyst here. We talked about catalyst in the past. Typically, that catalyst is palladium, Pb. Okay? So when you add H2, it's going to look like this. Okay?
Will you move the paper up?
Sorry. Okay. So I'm going to add H2. It's going to look like this. Now what happens is this double bond breaks. Okay? Half of it goes there. The other half goes there. This bond breaks. One of the H's go right there. One of the H's go right there. And I would simply end up with that. And now it's no longer an ene. It's been hydrogenized, and it's now saturated. That was supposed to be a D. It is now saturated with H's. This is what is called unsaturated, and this is called saturated. Does anybody know, like in real life, where that applies? Yeah, fats, right? You have, and they get even more complex. You've got, mono unsaturated, diunsaturated, polyunsaturated. Does anybody know the difference in these? Where they applied? No?
One is solid at room temperature, the other is liquid.
Do you know which is which?
The unsaturated is liquid.
Exactly. So
Yeah,
unsaturated is liquid. These are like your vegetable oils, your canola oils, things like that. Saturated is when you have things like what? Butter. Crisco, lard. Does anybody know what lard? Does anybody in here even know what lard is?
It's animal fat.
Yeah, okay. It's like when I was a kid, we killed all our own animals. You know what I'm saying? We raised them, we sent them to the butchery, cut them up. Every time we got a cow or a pig back, we got a couple of big packages of pure lard. And you used it to make like biscuits and pie crusts and things like that. Okay? But yeah, so saturated, these are solid at room temperature, and unsaturated are liquid at room temperature. Okay? Just some things you need to know there, right? Now, that's hydrogenation. I break the double bond, I put an H on each side, it becomes saturated. Okay? Now,
Hey, last year's video said that another catalyst was sulfuric acid.
okay, now, that is in a minute. Was that under the hydrogenation category? I think, Tomo, when I did that, I was just giving them a list of catalysts. Okay? I'm going to be a little more specific today because that was like a day one, a general overview. Does that make sense?
Yeah.
But you're right. Sulfuric acid is a catalyst in a minute. Okay, great question. Now, from hydrogenation, they're going to cover what is called halogenation. Now, we've actually already done halogenation. We did a little bit of halogenation in the past, or did we do hydrohalogenation? I don't remember. But it's the same idea here. So let's say I stay with the same. I got butene here, right? Now, halogenation is I'm going to add a what? A halogen. Now, for what they did in this book, they only did two. They did Cl2 or Br2. That's it. Those two, that's it. Okay? So, you're going to get the same thing. You're going to have Cl bonded to Cl, or you're going to have Br bonded to Br. Okay? This bond is going to break. It's going to open there, and it's going to open there. You're going to get one Cl there and one Cl there, and you would end up with something that looks like this, and you would end up with a Cl and a Cl like that. Okay? And halogenation does a couple of things. It will, let me think of an example. Okay, this is kind of like what they do. It's a little different, but this is like how they make Splenda. Does anyone know what Splenda is? Yeah, it's like sugar that's not sugar, right? What they'll do is they'll take sugar and they'll replace one of the O's with a chlorine molecule. Okay, and what that does is it halogenates it. But what it really does is it tricks your body into not recognizing it as a food source. It's like when you eat sugar, your body recognizes it as an energy source because it recognizes the molecule. When they make Splenda and they halogenate it by throwing a chlorine in there, your body looks at it and goes, that kind of looks familiar, but not really, so it doesn't use it, and that's why it passes right through you. It's kind of an amazing premise as to how that works, but that's basically what it does. Does that make sense? At all? Yeah? Okay. That's real loose, but that's kind of what happens there. Okay? And halogenation works the same as hydrogenation. You simply add one of each and you're done. Okay? And as I said, they call it halogenation, but they really only focus on these two elements, these two halogens. You don't see any fluorine and you don't see any iodine there, mainly just chlorine and bromine. Does that make sense?
Yeah.
Okay. All right. Now, those two are easy because I'm adding the same thing. H and H and then ClCl or BrBr. It changes when you start adding different things. So, for example, the first thing we're going to come to is what is called hydrohalogenation. Okay? Now, these are just hydrohalogens. Well, if you think about the word for hydrohalogen, what do you think we're doing? What would be a hydrohalogen? Nobody? Well, it's probably got a
halogen with a H bonded to it.
Yes, so I'm going to be HCl or HBr. Okay? Now, let's say I start out real easy. Let's say I start out with, let's go with propane. So I got propane, right? And I'm going to add, and it doesn't matter which one of these you do, but let's say I went, it's got to start with an H. Let's say I go here, and I've got HCl. So this is hydrohalogenation. Now, still the same thing's going to happen here. This bond is going to break. Half of it's going to go there. Half of it's going to go there. Now, anytime, now notice how these are now different things. One's an H, one's a Cl. Anytime you get, and everything after this, because the first two are the same, hydrogenation and halogenation, I'm adding the same thing. It doesn't change. These are now different. When I have things I'm adding that are different, they introduce you to what is known as Markovnikov's rule. Okay? Markovnikov's rule is pretty simple. Not the way the book teaches, the way I'm going to teach it. I teach it as the rich get richer. Okay? Now what that means is it means that the carbon that has more H's gets the H. The one that has fewer H's is going to get the Cl. Okay? So when I go back and I look at this, and this would be propene, right? If I were to draw this out, okay, does this carbon over here matter? Yes or no question there? No, because it's not where the bond's going to happen, right? It's only the two that are right here. Now, if I were to draw this completely out, this carbon right here is double bonded to that carbon, single bonded to that carbon, so it has how many H's right now? One H. This carbon is double bonded to those two, so it actually has what? It has two H's, right? So, if the rich get richer, this H is going to go right there. That Cl is going to go right there. Okay? So now when I draw this out, it's going to look like this. H, 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 H. That's where that Cl is going to go. Does that make sense? You see how I say the rich get richer, in that this had two H's, so it gets the H. This only had one H, it gets the Cl. Hello? Anybody? Okay, alright. Now, let's say I did this. Let's stay on the same thing here. Let's say I did this. Let's say I did this. Okay. I add HBr to that. Okay, now. So all I'm going to do is I'm going to go through, I'm going to look at this and say, okay, right now, this carbon is bonded to one, it's got 3 bonds, so it's going to have how many H's? It's going to have one H. What about this carbon? It's going to have one H, right? So in this situation, does it matter where the H goes and where the Br goes?
No.
It doesn't, because they each have one H. Okay? So just to understand that I've still got to look at this and say to myself, self, does one have more H's, then it matters. If one doesn't have more H's, then it doesn't matter. It's still going to split. Parts going there, and I could do either. I could throw the Br on there, and I could throw the H on there, or vice versa, doesn't matter there, okay? Most of the time, to illustrate this point, they will do it the right way. But I just wanted to show you that sometimes it doesn't matter. Most of the time they're going to write it because obviously it's homework and it's test stuff. They're going to write it to make sure you understand the rule. But there are situations where it doesn't matter. Does that make sense?
Yeah.
Okay, alright. So that is hydrohalogenation. Now, what was next on my objectives? Anybody know? Anybody remember what the last one was? Hydration. Okay, well, what do you think hydration is?
Water.
Yeah, I'm going to add water. I'm going to add. Now, we always write it as H2O. I want you to think about it as this. I want you to add HOH. Just like that. Okay? So, let's say I go back to something easy here. I got propene here. And I'm going to add HOH. Just like that. Okay, now again, this bond's going to break. Half of it's going there. The other half's going there. This bond's going to break. What is going to go where?
H is going to go to the one that has the most H's.
So where's it going to go?
On the bond to the right.
So it's going to go right there, right? This is going to go right there, correct? And what I would end up with, so I would have this, right? And that's going to have a bunch of there, and then I would just have that like that. Does that make sense or no?
That makes sense.
Okay. Now, here's something interesting. I don't know if anybody would know this. Is anyone in here? Oh, wait. Okay. Tolman, this is where you would stop me and say you're forgetting something, Mr. Denton.
Oh, you're forgetting something, Mr. Denton.
I am. You know what it is.
Let me see. Oh, wait, is this where we're talking about the sulfuric acid?
Exactly. This is the catalyst here. Catalyst. And in this one it is H2SO4. This is where the catalyst comes in. Okay? And typically that catalyst is sulfuric acid. Okay? I believe it's the only strong acid you can use there is sulfuric acid. So really we're talking about two catalysts. We're talking about sulfuric acid for hydration, and then we were talking about palladium for hydrogenation, correct? I think they're the only two. Yeah, I think they're the only two they look at. I'll have to go back over the test again and make sure, because those questions are kind of spread out. But I'm pretty sure they're the only two they worry about. Is palladium for hydrogenation and sulfuric acid or H2SO4 for hydration. Now, here's a question. Anybody know what the name of that would be?
Is it an alcohol?
It is an alcohol. It is. That's good. That's really good, actually. Take a stab at that, Sierra. Where's the alcohol? Where's the alcohol at?
In the middle.
Close. It's on the second carbon. So this would actually become 2-propanol. But I got to tell what alcohol it's on. It's on a propane, so it becomes 2-propanol, telling me that alcohol group is bonded to the second carbon. Okay? We're going to get into that, but that's for next time. Okay, we're going to get into all that kind of stuff. Okay? Now, what I want to do is I want to go through one of each edition and see if we can walk our way through it. Okay? That makes sense?
Mm-hmm.
So let's say I take this. So let's say I want to do that. Okay? I'm going to take, what's this? This is going to be 1, 2, 3, 4, 5, 6. So what would this be called? Anybody? Anybody know what this would be?
Hexene.
It's hexene. So I'm going to take hexene. Now why don't you have a number there?
It's on the 1.
It's on the 1, so I don't need it. So I'm going to take hexene and I'm going to add to it H2. Okay? Now, what am I going to get out when I'm done?
Hexane.
Hexane, exactly. I'm going to get out hexane because that double bond breaks, so it's no longer an ene. Correct? Okay? Now, the only thing you've got to remember here is what?
There's a catalyst on the...
There's a catalyst, and that catalyst is typically
PD.
PD, and they would write it just like that. Okay? Now, so what you're going to have this plus that, right? What's going to happen to that bond there?
It's going to break.
It's going to break. What's going to happen to my double bond there?
It's going to break.
It's going to break. Half of it's going to go there, the other half's going to go there, right? One of those H's... What?
Can you move your paper up?
Sorry. One of the H's goes there, the other H goes there, and I end up with just like that, and it basically just like that. Does that make sense? Or no?
Yeah.
Okay. Alrighty, so that's that one. Now let's go with halogenation, right? So let's say I take, let's say I just did that. I don't know if they'd ever go shorthand that much. And I'm going to add Cl2 to that, right? Okay. Now, what would this be trying to illustrate? Anybody know?
Ethene.
Yeah, that'd be ethene, right? That'd be ethene, right? I'm going to add to it Cl bonded to Cl, correct? Now, again, that's going to break. This is going to break, right? And I'm basically going to end up with this. If I had, they would probably never draw it that simplistic because there's just two. It would look like this, right? And then I would have a chlorine there, and I would have a chlorine there, and then I would have an H, an H, an H, and an H, right? Now,
Do you do the cis or trans on that, or no?
No, because there's no double bonds left. To be cis or trans, the double bond has to be remaining.
Okay.
Does that make sense?
Yeah.
Now, would it matter where I drew that chlorine on any of those spots? I mean, really? No, because remember, if you looked at that three-dimensionally, you wouldn't be able to tell the difference, would you? So if you go back, give me 1 second, guys. Let me show you something. I didn't think about this beforehand, or I probably should have had this already done. But I thought about it now, so I might as well hurry and whip it out, because I can. So if I go truly the way this looks, you know what I mean, it would look like that, correct? So these are my black carbons, then I've got my yellow hydrogens. I don't know what color chlorine is, but I made it green. Okay, you probably can't see that. But it doesn't matter where that's going to be because that single bond can twist, right? So it could be at any one of those spots and it wouldn't make any difference. You see what I'm saying? So it wouldn't matter how I drew that, okay? My question is, though, is there anyone in here that thinks they can name that? Sierra, you want to take a stab at it? I think you did the last one, didn't you?
I did, but I'm not too sure.
Okay, well, what has it got?
It's got 2 chlorine.
So that's going to be...
1 and 2 carbon.
Okay, so what's that going to be then? Because
would it be a dihalogen?
It would be, but I mean, if I was going to really name it, you're right, it's going to be 1,2 dash dichloroethane. 1,2 dash dichloro, 2 chloros, that's the 1, 2. And I have to go 1, 2 because I've got 1 on each, right? And I've got 2 of them, so I would always use numbers. So it'd be a 1, 2 dash dichloroethane. That's what that'd be called. Okay? Alright, so that's halogenation. What about hydrohalogenation? Hydrohalogenation. Let's say I took something more complicated here. Let's say I took that, I did that, and I'm going to add that to HBr. Now again, what's the one thing I've got to remember here? Anytime I'm now adding HBr, which means the 2 things I'm going to add are what? Anybody? They're different. So what do I have to remember here? Yeah, I got to remember Markovnikov. So I got to remember Markovnikov's rule. Okay, rich get richer, right? So this is going to break, right? Half of it's going to go there, half of it's going to go there. What is going to go here? What is going to go there? What's going here?
Bromine.
Bromine. There's going to be bromine. What's going to go there?
Hydrogen.
Hydrogen, right? Because this one already had 2 hydrogens, thus it gets the 3rd. This one only had 1 hydrogen, so it gets the bromine. And I would actually end up with this. And it'd look just like that, right? Anybody know what that's called?
2-bromo hexane.
Is he right?
Yeah.
Yeah, exactly. Okay, good job, Tolman. Okay. And then the last thing was what? What was the last thing we discussed? Wasn't it hydration, right? Let's say I went back to pentane. So let's make this a pentene, right? I'm going to add HOH like that, right? That's going to break, that's going to break. Half of it's going there, half of it's going there. What's going to go here?
The OH.
The OH. That's going to be my H, right? Rich get richer. Boom, boom. Now, what would that be called? Anybody?
Pentanol.
2-pentanol. Just like that. 2-pentanol. Because it's on the 2nd carbon. What makes it what it is on the 2nd carbon, which is why I number that.
Denton, I have a question.
Yo!
What would you do if there was 2 double bonds?
Okay, so that's a great question. We are forgetting something here. First off, anybody know what we're forgetting here?
Sulfuric acid.
Catalyst, remember, H2SO4. Don't forget your catalyst. Okay, don't forget catalyst. Okay? Yeah. So, Myers, is that you?
Yeah.
Alright, now, if there are multiple double bonds, it kind of depends. Typically this is stuff that is done in the lab, or this is stuff that's done in industry. You know what I'm saying? So a lot of times you can't control where that bond attaches other than you know it's going to Markovnikov. So like if I had this, let's say I had this, and I had that, and I had that. Let's say they were my two options.
You gotta move your paper down.
Sorry. Let's say this is what you're asking, right?
Yeah.
So something like this. Now, what you'll notice, and I don't think they even address this in the text, again, because this is early on. You can't guarantee which one of these is going to break, or if what happens. What could happen?
Both of them break?
Yeah, they could both break, and I could have two of these. You know what I'm saying? So it just kind of depends. So what they'll do is they would actually do this, see what happens, and then filter out your product. So what you would get is you would get this. You could get this going on. You could have that stay, have that be an OH, and have that be an H, right? Or you could get this. Now here, these are going to be the same, right? So you could have an OH there and an H there. Or you could get this, have an OH there, have an OH there, and have an H there. What you would learn is that these are going to be vastly different compounds. What they would do is they would go and sort these out, like through a distillery or through oh my gosh, it's a column. It's called wow. The name is no, but they use this big column, and the gases come off at different temperatures. And after the life of me, can't remember what it's called now. But it's like in a refinery. Okay, and what they would do is that each one of these are going to have very different properties, and they would go and they would fraction it out, and they would figure out which one's the most, and then that's what they would do. But you can't guarantee which one of these you're going to get. You would do it, and then determine what you get, which one happens the most. Does that make sense? And you'd kind of go at it from there. If they only wanted one thing, they wouldn't do something like this. They would say, we're going to just put this one in. That way we know what we're going to get out. Does that make sense? They wouldn't do it where they didn't know absolutely sure what they were going to get. So yeah, you would probably not see this in the test scenario because you don't know what's going to happen. You're going to see this because I know exactly where that bond's going to break. I know exactly where my addition things are going to go. You see what I'm saying? So yeah, this you won't see. You won't see any of this on the test. This you'll see on the test. Because here you just don't know. So that way they're not going to put it on a test question because any of these could actually be correct answers. Okay? Okay. Anybody else? Got a question? So we covered we covered hydrogenation, we covered halogenation, we covered hydrohalogenation, and we covered hydration, correct? They are the four main ones you're going to need to know. Okay? Now what this does is it gives me 2 more days to cover the last 5 sections. Okay? And we're going to do the last section. So we're going to do section 13 all by itself. So next time we're going to cover polymerization. And, oh, no, we're not. No, we're not. Yeah, we are. We're going to cover, let's see, 8, 9, and 10 next time, and then we'll cover 11, 12, and 13 the last day. Then that gives us 4 days on this chapter. Alrighty? Questions? Sydney laid on here? How about Hannah Staley? Negative? Trey, you're on here, right? Negative?
Yeah.
Good job. You're one of the first 3 to do all the Learn Smarts. You and Hannah and Sydney were at. What number are we at? Anybody happen to notice what number we got to?
55, I don't know. 56 is the highest I caught.
What the crap, man? I'm not done teaching. Where are you going? Man, teenagers, gosh. Okay, any questions?
I have a completely unrelated question.
Okay.
Can we synthesize a vitamin?
What?
Can we synthesize vitamins?
Oh, yeah. All the time. Yeah. Most of the time, though, they're actually extracted instead of synthesized. So they'll take something, they'll extract the vitamin they want out of it. Do you know what I'm saying?
Yeah.
And so, and then if they can't do that, they'll often try to condense it. They'll take the desired vitamin, pull all the vitamins out, and then just condense them down into, are you talking like supplements, things like that?
Yeah.
Yeah. They'll condense them down and pull them out, like I don't know. Let me think of a good one. Was there a question there? No? Like vitamin C. Vitamin C is just ascorbic acid. That's something they're gonna make rather than taking a bunch of oranges and trying to extract them, because oranges are used for other things. You know what I mean?
Yeah.
So that's something they would just go in the lab and say, hey, we can just make a bunch of ascorbic acid and sell it. Or not ascorbic acid, sorry, citric acid. Citric acid. And then you can just sell it, you know what I mean, rather than trying to buy all those oranges and condense them down and extract it. That'd be pointless. Some things, though, you have to get that way. There are a few things that are hard to make, synthetically in the lab that are easier just to go and extract from a fruit or extract from a plant. But the way chemistry is now, there's very few things we cannot make. What it boils down to is to cost usually, which is cheaper. Is it cheaper to go in the lab and synthesize it, or is it cheaper to buy a bunch and extract it? Does that make sense?
Yeah.
So it just depends. Okay? Anybody else? Not a soul? All right, I will see you guys on Wednesday, okay?
Yeah.
Okay, talk to you later. Bye, people. Bye. Yeah, it's a little creepy. Allison, you still there?
Oh, yeah.
Did you get your Chromebook stuff fixed?